you have it with you? So after I go through some questions, I want to say one more thing about internal loads, and then I just want to have you work on the board in groups. Number 4, did you say? 3, which one?
If you could do either A or B,
okay.
B is probably more beneficial.
Okay, B. See, look, I got my little, made my little taskbar here. Let me know if, I might have to make the fonts a little thicker, but let me know if you have trouble seeing any of the stuff I write. Okay, so this is internal loads. Can you all see that okay? Number 3B. There's a fixed joint at the left.
Oh, I had a question. A quick question. Just
oh, that's C. Yeah.
From Thursday, I wasn't here. I was just wondering if
oh, yeah. Have I not? I guess I just forgot to do it. Sorry about that. You know what would be really helpful is if you sent me an email later today, and then I'll remember to do it. Otherwise, like, sometimes I'm surprised even by now I still remember what conversation we were having. Have you seen the movie Memento? That's like what I'm like. I like have tattoos that say like, can you post the video for Tuesday or whatever? Okay, B. Okay, so B looks like this. You have a cantilever over here. And a distributed load over the right half. And this has a magnitude of 25,000 newtons per meter. And a force vector over here of 25,000 newtons. And this angle is 45 degrees. And this is half a meter. And this is half a meter. Well, since the fixed joint, the only joint with the outside world is on the right end, and when we do our cuts, we never get to all the way to the right end. So we don't have to do that calculation of external loads. We can just get right into the cuts. There's no weight mentioned in this problem. And so when we're looking for the key points to analyze, there's the endpoints. And then right in the middle, the function defining the distributed load changes. And so there are 3 of these key points, and that means that we're going to do 3 minus 1 cuts. Okay, so the first cut is for x values between 0 and 0.5. All right, this is a force vector. I can't remember what that number is, but 45 degrees, so we have a positive. It's like 17,000. What's 25,000 times? 677.7, and then negative of that. 0.7. Why did I write a 5? Okay, so that's the force vector. I think that my other software I used had like some smoothing stuff going on. You know how to access that? It makes me feel like I have like really bad Parkinson's.
You know, if you zoom out and you increase the size of
Mm-hmm.
what you're writing, if you can
Oh, okay.
pull back a little bit,
Uh-huh.
it does smooth out.
Huh. Okay. I'll try that later on my own time.
Yeah, maybe try the newer version too, because it's 2016.
Mhm.
It's good for some older
Yeah.
functions that they have, but if you use like the newer one, they're constantly updating it.
Uh-huh.
And I'll show you.
Okay. So, and then the internal loads T, V, and bending moment. So Newton's second law says 17,677.7 negative 17,677.7 plus T negative V is equal to zeros. And so T is equal to negative 17,677.7. What does the negative mean there physically? If you have a tension of negative, that means that this part of the beam is in compression rather than tension. Okay, so the length would be, you always get some amount of deformation due to this loading. And in this part, that's going to be contracting a little bit rather than stretching. And the shear force is also negative 17,677.7. So those are constant over this whole part. And now we go to the moment equation. The about point, like always, for me is going to be at the left. Come on, you. And so the only things that produce moments are the couple m, and then minus Vx, and that's equal to 0. So m is equal to Vx, and V is negative 17,677.7 times x. And so that's the function for the bending moment. And so these are the subfunctions that are valid on the interval x between 0 and 0.5. And now we'll go to cut 2. And this is representing x values between 0.5 and 1. This time we have some amount of that distributed load. And we have the force vector over here. I think I have those signs backwards. Come on. The whole length is x. The length of just this piece is x minus 0.5. And then we have the internal loads. So let's figure out what we can say about this rectangular distributed load. It has a height of 25,000 and a width of x minus 0.5. And the centroid is right in the middle. The area of this rectangle is the product of the width and the height. So that's 25,000 x minus 12,500. And so I'll redraw this free body diagram now with the distributed load represented as a point force.
So we wouldn't need to, from my recollection, it's 25,000 Newton meters, right?
Newtons per meter, yep.
Okay. And we wouldn't need to change it.
Right, this is Newtons per meter. This is in meters. Multiply those two together and it gives you Newtons. So we have a downward force here with a magnitude of 25,000 x minus 12,500. And we have these forces, 17,677.7, negative 17,677.7, and then the internal loads. And the one other thing we're going to have to do is figure out the location of this point force. And the way I like to think of that location is, since this is a uniform distributed load, I'm just going to take the average of this and this. Okay. So the distance from the left end to the left part of that distributed load is 0.5. Okay. The distance from the left end to the right end of that distributed load is x. So the centroid right in the middle is just the average of 0.5 and x. You can think of that as the quantity x plus 0.5 divided by 2. You know, that's just taking the average of those 2 points. So this distance is x plus 0.5 quantity divided by 2. Mm-hmm.
It'll allow your quick tool bar
Mm-hmm.
to display. And then, but then you could modify like the size. So you could like move it over.
Yeah, get rid of all that stuff.
Like the bar on the right.
Okay, I'll fiddle with that. Okay, so Newton's second law says 17,677.7, negative 17,677.7, plus this downward force with this magnitude. And that means that we're going to multiply this magnitude times a unit vector of 0, negative 1. So this, as a force vector, is going to be 0 for x, and then negative 25,000 x plus 12,500 plus t negative v is equal to zeros. And so t is the same thing it was before, negative 17,677.7. And v is equal to negative 25,000 x minus 5,100 to where am I? 5,100 27.7. Is that right? Okay, and then we'll go to the moment equation. Again, our about point is this. It's weird. I have, like I said, every single class, there's some new stuff that comes up. I haven't seen this one before, but
You must have moved it over.
yeah. But I haven't seen the thing where it, I haven't seen this thing where it won't give me the toolbar all of a sudden. It was always doing it pretty well before. Anyways, just bear with me. So the moments, we have a force of 25,000 x minus 12,500 times that moment arm. And would that make it rotate clockwise or counterclockwise? Clockwise, so it's negative, so negative x plus 0.5, and I think I'm gonna, so tell me if you don't follow this, but I'm just moving I'm multiplying these two things together. I'm gonna just move the 1/2 over to this one, so I don't have that 1/2 factor in there. So this is x plus 0.5 times 12,500x minus 6, 250. And then we have plus m minus vx is equal to 0. Multiply this out, and you get negative 12,500 x squared minus 6,250 x plus 6,250 x minus 3,125. Plus m minus vx is equal to 0. So m is equal to positive 12,500 x squared. The middle two terms cancel out. Minus 3,125 plus vx. So m is equal to 12,500 x squared minus 3,125 minus 25,000 x squared minus 5127.7 x. And so m, the final answer is negative 12,500 x squared minus 5127.7 x minus 3,125. And these subfunctions are valid on the interval between 0.5 and 1. Let's check the derivative relationships. dm dx is equal to negative 25,000x minus 5127.7. So dm dx is equal to v. That one works. And then dv dx is equal to negative q. So v is equal to negative 25,000. Take the negative of that. I mean, dv dx is equal to negative 25,000. Negative of that should be equal to q, and q is 25,000 on this piece. It was a uniform distributed load of 25,000 newtons per meter. And let's look for it on cut 1. dm dx is equal to v. That works. dv dx is 0. And on that first cut, there was no distributed load. So that one works. Any questions about that?
So Q is only on the distributed.
Yeah, if the cut that you're looking at isn't inside a distributed load, if those x values don't have distributed loads acting on them, then Q is 0. Any other questions? Okay. I want to show you something that is going to shock you and amaze you. Fill your hearts with dread. But then I'm going to tell you don't have to worry about it, so that's just, so don't worry about the dread part. Okay, so we've done a bunch of problems like this. So say you have a cantilever beam connected on the right. That's what you like to see because it lets you skip calculating the external loads. And then you have a triangular distributed load like this. That's a pretty simple problem. That's not too hard. So how hard could this be? It's basically the same, right? Well, let's think about the cuts. I'm not going to go through the calculations because it takes a long time, and I don't think it's really worth it. But let's think about the first cut. Remember, so this is the part of the beam that we're ignoring when we make that cut. Okay. And that means that we're ignoring this part of the distributed load. And then we have the internal loads. And so what happened that makes this hard, that makes this really a pain, is because of the orientation of that triangular distributed load, the cut we made took away its triangularity. It took away what makes it a triangle. So what makes these complicated is that making that cut means the distributed load no longer has a triangular shape. That's the solution. Yeah, well, that's the right idea. Yeah. That doesn't always work, but, and I'll show you why. But the way you have to do it is, so take that distributed load and represent it as a triangular distributed load sitting on top of a rectangular, okay? Then this is your function q of x, the height at that point. This is your total value, you know, let's say this is 5,000 newtons per meter. So this whole thing is 5,000 newtons per meter. And that means that this one is 5,000 minus q, okay? And you can now treat this as two separate distributed loads. This one has its centroid 1/3 of the way from the left end. This one has its centroid at x over 2. So this distance is x over 2. This distance is x over 3. And you can calculate all of these, you know, the I put that, I did that wrong. This is the one. So the height of this rectangle is 2, right? The height of the whole thing is 5,000. So the height of this triangle is 5,000 minus q. So this is the one that's 5,000 minus q. And now you can calculate how to treat these as point loads. The triangular one has a height of 5,000 minus q, a width of x. So the area of the triangle is x times 5,000 minus q over 2. The rectangle has a height of q and a length of x. And so the area of that rectangle is xq. And that q is a function that you know. So now you can figure out where, you know where the point forces go, you know the magnitude of the point forces, you can go through it, but you have polynomials for all of these things. You get higher order polynomials when you take the moments. It's really ugly, you know. And so what I would recommend instead is, so we're over here, we have the wall over on our right, and here are your footsteps. And you end up there. And now looking at this, you see a wall on your left and a cantilever beam and a triangular distributed load. And do this. Okay. So you're going to walk to the other side of the beam. And now it's easy to solve. So what about this? Let's say you have a cantilever beam. Okay. What about that? What's the solution for that? That's sort of a pain. Really, I would say just when you're doing the cut in this one, think of it from this side. When you're doing the cut that represents this one, walk to the other side and do it. Your x's don't mean the same thing, but you still have x's that represent every physical point. So as long as you're clear about what physical point on that beam a certain x value represents, you know, you can just always think of it from the perspective that makes it easier. Okay. So for this one, just take the view that makes it easiest for each cut. Just remember that your x values don't mean the same thing. I think on the set of internal loads problems that I gave you, I think there might be one problem like this, but I'm not going to make you do it. I don't think you probably ever in another class in your life will ever see something like this. And you certainly would never see something like this without them sort of reminding you how to do it. So just forget it. That's wasted brain space. Use that brain space on something else. Okay, anybody have any questions about that? So remember, with any problem, you can always just walk to the other side of the beam if it makes it easy. This is the only case where I can think of where it makes it considerably easier, but you can always just take a different view of it. All you're trying to do is come up with a relationship between x values that represent physical points on the beam and some kind of function, you know. So it doesn't matter which way your x goes or anything like that. Okay. So now, let's say we have a beam with a pin over here and a roller on the other side, and a horizontal force here of 5,000 newtons. And the weight of the beam is 700 newtons. And let's say the length is 2 meters. Calculate the internal loads. Do the derivative checks. And graph the T, V, and M functions. Okay, and do this in groups. Write your answer up on the board. You can do it back there and then come write it up, or just work up here. If you work up here, I can see what you're doing the whole time and help you with mistakes you might be making. So that's what I would prefer. But if you want to work it back there and then come up and write it up, that's fine with me too. And after you're done, I'll go through it. Okay, go ahead.